Okay, so I think we were here yesterday, right? We were talking about different ways to separate and isolate proteins. So this is kind of a summary table that would be good for you to review from in terms of the principle of different uh, techniques. But what I'll do is I'll go over each one of them separately. So if we look at precipitation for protein isolation based on solubility, differences in solubility, one would be using salt. So using salt is a common way to separate protein from a matrix. So you can either use salt to solubilize the protein, but if you want to precipitate them out, you can use salting out technique. So I confused you. So there is salting in and there's salting out. And I don't have the salting in here. So we can salt in first. And that is the extraction bit. So if we look here, we have the extraction. One way to extract protein from a complex system is to solubilize it first. We can solubilize it by salting it in, or we can solubilize it by choosing a pH that will solubilize the protein best. Okay? So the first step is salting in. That means add a little bit of salt concentration. It depends on the protein. Some protein require 0.1 molar salt, some proteins require 0.5 molar. So it really has to do with trial. First, trying to see which concentration of salt will give you the maximum solubilization of protein. So let's say we have a flour, like from pea flour, for example. So in pea flour, what do we have potentially other than protein? What do you think the composition of pea flour is?
Starch.
Huh? Starch, definitely. What else? Very small concentration of lipid, less than 2%. Fiber. So you have protein, you have fiber, you have starch. These are the three main components. So I want to take the protein and solubilize that. So I can prepare a solution of salt and put my flour in it. And that salt will help the protein to go into solution, into the aqueous or the aqueous phase, basically. So, and then what will precipitate if I centrifuge, that would be the starch and the dietary fiber. But when I salt in my protein, other components might get soluble as well. What components from pea might be soluble in salty water? I might have small sugars. I might have dietary fiber that is soluble. So whatever is in the salt solution might not only be just protein. So I want to further concentrate my protein. In order to further concentrate and separate it from other soluble, I will precipitate it. Okay? So I want to precipitate only the protein, so I use salt, a different type of salt, at high concentration to precipitate the protein. How would that happen? So if I have a protein that has a net positive charge at neutral pH, what I will do if I add ammonium sulfate, the ammonium sulfate, especially the sulfate ions, will interact with the positively charged group, shielding the charges. So instead of the protein interacting with water and repelling each other, you will be shielding the charges with the salt, and the salt will be competing for water. So now the protein will aggregate via hydrophobic interactions. Because now on the surface you don't have any more repulsion. The salt has shielded your net charge. Therefore, they will come together via hydrophobic forces due to the hydrophobic residues that could be on the surface of the protein. So they will come together, aggregate, and precipitate. So if you have different proteins in in your solution, in your salt solution that you have prepared, and you're targeting a particular component. Because, you know, when you have pea protein or soy protein or whey protein, it's not one type of protein, it's multiple types of protein. Sometimes you want to target one subunit of protein. You can do that by changing the salt concentration, by selecting different salt concentration. For instance, if you have 5 different proteins in your solution and you're interested in one type, let's say type C, and if you look here, it have increasing net charge from A to E. So E has the highest net charge and A has the lowest net charge. Using salt, how can we isolate C? Just think simple terms. What would you do? So the higher the net charge, the more your salt concentration you need to precipitate it. Okay? The lower the net charge, the less salt concentration you need to precipitate. So what you would do is you put in salt just enough to precipitate A and B. C, D, and E would remain in solution. Then you centrifuge, you take the precipitate, discard it, then take the supernatant, then add a little bit more of salt, just enough to precipitate C. Okay? So in order to design an extraction like that, an isolation like that, you really need to know the components that you have in your solution. You need to know the different net charge of the proteins at a particular pH, and you need to start doing trials to see what ionic strength is going to get me to precipitate A and B first, and what ionic strength will precipitate C next. So usually it takes a lot of trials in order to figure out the concentrations. Okay. So precipitating by isoelectric point. Let's say if you have milk and you want to precipitate casein, separated from whey protein, then you bring the isoelectric point to 4.6. And then you can separate casein protein from whey protein. But sometimes you have, let's go back to the flour example of pea flour. Sometimes you need to put the protein in solution first before you precipitate it. So, and again, same as salting in first. Extraction, in this case, we extracted using salt. In this case, we extract using pH. So we can do alkaline solubilization. So the alkaline solubilization, for pea flour specifically, we can solubilize pea flour at pH 7.5 or 8. So I can solubilize the pea flour, again my starch and insoluble dietary fiber will precipitate. I take my extracted protein now from my first step of isolation, which is extraction. I take that extract, and then in order to purify it and remove any soluble sugars and dietary fiber, soluble dietary fiber, I can precipitate it using the isoelectric point. At the isoelectric point, your protein loses net charge. So it will have a 0 net charge. So in casein, for example, has a net negative charge at pH 7 with a net charge of negative 11. And it's interacting with water. Once I bring the pH to the isoelectric point of casein, for example, to 4.6, so I lose the net charge, so there is no repulsion anymore, no minimal interaction with water. The proteins come together via hydrophobic interaction, aggregate, and precipitate. So in this example, it's casein. in the example I was talking about with first extraction with alkaline pH, that would be, let's say, P protein. What do we use? 4.5 is the isoelectric point. We can use isoelectric point of 4.5 to precipitate that particular protein and separate it from soluble sugars and soluble dietary fiber. Okay. Another way to separate using differential solubility is by solvent extraction. So with solvent extraction, you're basically using precipitating the protein with an organic solvent. In this case, if we add acetone to a protein in water or in an original extract that we got the protein in an aqueous form, then I want to separate it from other solubles and concentrate it. I can add acetone. The acetone basically replaces water by interacting with the charged surface. And because it's an organic solvent, the hydrophobic residues within the inside of the protein will be exposed to the acetone because they like hydrophobic solvent. So the protein opens up, exposes its hydrophobic components to the solvent, and since now we have hydrophobic components exposed from multiple proteins, they would attract each other and they will aggregate and precipitate. Another way of separating based on solubility is by denaturing the protein with heat. So if we denature and also with pH, extreme pH result in also denaturation of the protein because you would have like charges on the protein and the protein starts opening up. Instead of the residues interacting with each other with like charges, they start repelling each other and then the protein opens up. And once the protein opens up, again, it will be attracted to each other via hydrophobic interactions, and then they aggregate and precipitate. And isolation and precipitation using protein denaturation is not desired because in this case, you are truly isolating the protein, but you are changing its structure in a way that could be detrimental for functionality. What I have here is just to demonstrate if we want to separate proteins from milk, the casein and whey protein from each other, we can look at the denaturation temperature difference. So casein is stable at 140 degrees C, whereas whey protein denatures at 70 degrees C or higher. So if we heat for an extended period of time around 70 or 75 degrees C, the whey proteins will aggregate and precipitate, and we can separate them from the casein. Now, why the casein is more stable to heat than whey protein? If we look at the structure, anything that has a defined structure has tendency to be deformed by heat. So whey protein has a defined secondary structure and has a globular tertiary structure. So changes in heat will impact the interactions that you have. So if you have high temperature, hydrogen bonding electrostatic interactions might be broken. And also think about the kinetics. We'll talk about next week, I believe, the impact of water on protein denaturation. So when we heat, water movement becomes faster, so the kinetic of the movement of the water becomes faster, goes inside of the protein and breaks the bonding. So it interferes with the hydrogen bonding, for example, that is within the protein itself. So the protein unfolds, opens up. But if we have an open structure protein with minimal secondary structure and tertiary structure, it will be less impacted by heat because you don't have as much compact and close by interactions within that protein compared to a globular structure. So therefore, random structures that are not very ordered structures, they are more stable to heat than a very ordered structure that is stabilized by a lot of different bonding. Okay. You can interrupt me for questions, or if you want me to repeat any concept. Lisa, yeah.
On the previous slide about acetone, you said it replaces the water by interacting. So does that just destabilize it?
Yeah, it destabilizes because now the acetone is in direct contact with the protein itself, and the hydrophobic residues will start orienting themselves to the acetone because it's hydrophobic. Originally, they hide from water, so they're inside. But when they have acetone in their proximity, then they open up, and because they want to interact now with the acetone. So the protein unfolds, the hydrophobic residues are interacting with acetone, but another group also has hydrophobic residues exposed, and then when you have multiple proteins in the proximity and all of them have hydrophobic residues exposed now, then you have very strong attraction due to hydrophobic interactions, and then they come together.
So they prefer to bind to each other than to the acetone?
At that point, the hydrophobic interactions between the residues become strong. Yeah. Good, very good. Okay. So here's an example of use of differential solubility to isolate actual ingredients. We talked about the pea protein example, but here in this example I have soy flakes. We start off, in soy it's different than pea because you have fat. First step you want to do is remove the fat because it interferes with isolation of the protein, with the solvents to isolate the protein. The fat will be in the way and it will hinder the extraction of protein. So the first step is removal of the fat, and usually we want to bring the fat content to 2 to 3% to avoid interference and to maximize extraction of the protein. So we start off with the defatted soy flakes, and from there are two routes. There is a route to produce a concentrate and a route to produce an isolate. So both are based on solubilization. So here, for example, if we add alcohol, aqueous alcohol, 80%, or water wash, just water wash, what happens here is you remove the soluble sugars and the soluble, it's oligosaccharides, soluble sugars and oligosaccharides. And then you end up with dietary fiber and protein. So the soy concentrate is 65% protein. You still have quite a bit of dietary fiber in here, mostly insoluble dietary fiber. So the soy flake is about 40% protein, 40 to 45% protein. When you remove the sugars and the oligosaccharides and some soluble dietary fiber, you concentrate the protein, but you still have some dietary fiber insoluble in there. That's why you go from about 40 to 45 to 65% protein. So we call that soy protein concentrate. So the soy protein concentrate can be used in so many different applications. A common one is extrusion to produce texturized vegetable protein. To produce an isolate that is 90% protein or greater than 90% protein, that's when you want to solubilize as much protein as you can using alkaline solubilization. Again, about 7.5 to 8.5. If you want to reduce oxidation and if you want to reduce color change and denaturation of the protein, you go with the lowest alkaline pH possible, which is about 7.5. But that will reduce the yield a little bit for you. So the first step is the extraction of the protein, and then now you have the solubles. You have the protein, you have some sugars, oligosaccharides, soluble dietary fiber. You want to purify it more, like I said, the precipitation at the isoelectric point. So this acidification is really precipitation at the isoelectric point. And then you do several washes and neutralize, because you never want to dry a protein at the isoelectric point. You want to make sure that the pH is not where you have net zero charge, because that impacts the functionality of the protein on the long run, causes denaturation at lower temperatures, and that would result in polymerization, and that will result in detrimental functional characteristics. All right, so we neutralize and then spray dry, and then you get the isolates. So here, when we do acidification, there is a centrifugation step, basically, and you wash again, and then you centrifuge. What happens is your solubles that were not protein will remain in the supernatant, and you discard, and the precipitate where you have your protein, you wash it a couple of times, then neutralize it, then you spray dry. And that's what happens in industry. There are some disadvantages when you use pH, increase the pH, and then decrease the pH. What are you generating in your ingredient? When you have NuH and then you add HCl, salt. So oftentimes the ash content can be high here, unless they want to put in the extra expense to desalt. So they run it through a membrane or do diafiltration to remove the salt, basically, to reduce the ash content. Reducing the ash content can get them to a higher claim of protein, and also to, the more pure the protein ingredient is, the higher the functionality of the product. Okay. Separation by adsorption, and this is basically chromatography. I think I gave you the example of whey protein isolate from Agropore last time, did I? Yeah. So this is a whey protein ingredient that is produced by ion exchange. That means what they do is they take the whey that comes out of as a byproduct of cheese production, and then they run it through a membrane to remove lactose, not a membrane, sorry, run it through ion exchange to remove lactose, reduce the calcium content, and purify the protein. The end product is highly functional and has better solubility, and it's high in beta-lactoglobulin compared to a membrane isolated whey protein isolate or concentrate. So the principle here is separating based on charge. So we can have anion exchange or cation exchange depending on the charge of the protein that you are separating at neutral pH or pH that will give the protein a charge without impacting its structure and functionality. So if a protein has a negative charge at pH, let's say neutral pH, then what you would do is you would use an anion exchange chromatography. And that, I'm not going to cover the principle in detail here. If you've taken analysis recently, you should remember that with anion exchange, that means we're exchanging anions, and you have a positively charged stationary groups, and then cation the opposite. If the protein is positively charged, then we're doing cation exchange chromatography. And for separation of protein, the resin in the column usually is a polysaccharide based resin, because you want large pore sizes to allow large proteins to move through your stationary phase. And then what happens here, the hydroxyl groups on on the carbohydrate moieties will be derivatized into either an acidic group or a basic group. If it's an acidic group, that means it carries a negative charge. That means it separates positively charged proteins. If it is a base group, it has a positive charge. That means it's going to separate negatively charged proteins, because the negative will interact with the positive, and the positive will interact with the negative functional groups. Of course, I have 4 lectures on chromatography and food analysis, so I cannot cover that here in more detail. If you have questions, I can give you the chapter and my notes to review for chromatography.
Why don't we use absorption over the solubility separation?
Okay, so that's a very good question. So if I go back to the Agripor example, they have a patent on anion exchange, and they had it for so many years that nobody other than them in the States can use that anion exchange chromatography to separate their whey protein. And they had, for the longest time, the most expensive and the most functional protein. So it's more expensive to have column chromatography to isolate a protein, but at the end of the day, you get a really good functional protein and you get more money. I mean, so it would be more expensive. So basically, it depends on feasibility and how much money they want to invest in the production of their protein isolates. Okay. Good. A very common separation and isolation of a protein is hydrophobic interaction chromatography. But this is not done in industry, as far as I know, because of the amount of salt that is needed for this procedure. Okay, so what's the principle here? It's same with salting out in solution, but instead of salting out in solution, you prepare your protein. You have your protein extract. It could have, protein extract has some soluble sugars in it, and you want to remove the soluble sugar and soluble dietary fiber, and you want to purify your protein. So you prepare your sample in a very high concentrated salt. In this case, in this example, 2 molar ammonium sulfate. And what happens, but from its name, it's hydrophobic interaction chromatography. So your stationary phase have functional groups that are hydrophobic. So the red denotes hydrophobic groups. And then when you salt out the protein now you shield the charges by salt. Then the hydrophobic groups on the protein can now interact with the hydrophobic surface because they're no longer soluble. Okay, so they will basically precipitate on the column, on the stationary phase, and interact via hydrophobic interactions. All right, and then if we have multiple types of proteins in there and they vary in their surface hydrophobicity, okay, the most hydrophobic will interact the most, and the least hydrophobic will interact the least. So when they leave the column, the least hydrophobic will leave the column first. So the most polar on the surface will not really precipitate as much on your column. It will just move faster through the column. Now, but the most hydrophobic is going to interact and linger on the column, and the way to get it out is to decrease gradually the salt concentration. Hi, Katie. So you reduce gradually the salt concentration all the way to water. So in this example here, what we have is we have mixed protein and carbohydrate to induce Maillard reaction, and to add a sugar to the protein to change the function of the protein. But then there were still some free sugars that we wanted to remove. So the way we do that is with hydrophobic interaction chromatography. When we run salt, the sugars will come out, They will not interact with the column. Your proteins will interact with the column. Then when we run water through the column, the protein comes out. In this example, we're measuring absorption. This is basically chromatography linked to UV detection at 280. So we measure absorption, and we can monitor when the protein comes out. So this, when you have an absorption at 280, that means you have protein. So you can see here in the salt, we have a little peak. And then in the water fraction, when we put water, most of the protein came out. So most of the protein in my sample has a high level of hydrophobicity on the surface. So these that came out sooner are very hydrophilic peptides that did not like to interact with the column. So we lost some peptides here, some hydrophilic peptides, but the majority of the protein we were able to separate from our sugars and collect as a purified fraction. We can play with the gradient to gradually decrease the salt from 2 molar to 1.5 to 1 to 0.5 to water. Then we can separate different fractions within the protein. If we're really looking to separate proteins fractions and collect different components, we can do that by gradual elution or gradient elution. Okay. This is not highly used in industry. It is more on a research scale or more pharmaceutical scale. If I want to produce purified antibodies, for example, or very pure antigens for an assay, for an immunoassay, I can use affinity chromatography. And in this case, in affinity chromatography, the interaction of my protein of interest is very specific to the functional groups on the column. Highly specific interactions. So the ligand or the functional group, the blue triangle here, is can be an antibody for a specific antigen. It can be enzyme inhibitor for a specific enzyme that I want to isolate. Or it can be a general ligand, like lectin, that is specific for separation of glycoproteins. So once my protein target has been linked or interacts with the column, all of the other proteins that I don't care for or components that I don't care for will leave the column. For me to get this out of the column and collect it, I can change the pH and the ionic strength, so the bonding is broken, so this will move down the column. Or I can add these little triangles or ligands in my mobile phase. So if I add mobile phase with these kind of ligands in it, then this will start interacting with the ligands in the mobile phase, and it will leave eventually with the mobile phase. Okay, any questions?
After that, is that easy to make the ligand leave the protein well? Because finally, like.
Well, the interaction, yeah, you can change it by changing pH and ionic strength, so you can loosen the binding and you can separate them.
So the same way, like.
Yeah. Mm-hmm. Yeah. Okay. Any other questions on adsorption? So you can separate based on size. And it's a very simple form. I didn't bring it with me. Okay. I put it in my office and I didn't bring it with me. Are you familiar with dialysis? If you're not, can you raise your hand? Okay. Everybody else know what dialysis is? Yeah, what do you know about dialysis? Tell me. Huh? Okay, but in the laboratory setting, do you know what it's used? Okay. Anybody would like to explain dialysis? Go for it, Rachel.
Dialysis is a semi-terminal
So oftentimes, if we use salting in to isolate our protein, we need to remove that salt. Okay, there's a lot of salt. You don't want salt. You want to purify your protein. A very common method we do it in the lab is like it shows in the picture. I had my membranes and I forgot them in the office. But usually it's a tube that has different pore size, as Rachel was saying, and you can select the pore size. We can select as low as 500 Dalton and as high as 30 Dalton, kilodaltons. So the lower the pore size obviously will allow only small molecular weight components to leave the membrane. And usually what you do is you put your tubing with your sample in it and seal it like by clips here. You put it in water or buffer. And what happens over time, and you have a stir bar usually in there, and we like to keep it cool so that you don't grow any microbes in it. So we put it in the fridge, and then there's a stir bar that helps with the circulation. And then what happens is your salt will get to an equilibrium between the inside and the outside. So every 4 hours or 5 hours, we change the water or the buffer, and then you get to another equilibrium. And you continue doing that until the concentration of salt inside the tube is very, very small. You will never get zero, because the principle here is you reach equilibrium after a certain period of time. So you never get zero, but you reach a really low concentration of salt. And sometimes you don't only want to get rid of salt. This method can get rid of small sugars as well. So you can purify your protein extract even more. But oftentimes dialysis is linked to using salt to extract and isolate your protein. Sometimes the membrane is coated by polyethylene glycol to prevent water from going in, so that you don't get bulging of your over dilution and bulging of your tube. In industry, however, you don't use this form of dialysis. You use more like a filtration, yes.
How does using polyethylene glycol prevent bulging?
So the water won't go in, because salt will go out, but water won't. Because water can also migrate in and out. So if you coated the surface of the membrane with that, what's that? Glycol, then it won't let the water go in.
So how? It just doesn't.
It's a barrier. It just prevents it. Yeah, barrier for water. Immiscible with water. Doesn't like it. Yeah. Okay. So in industry, however, you don't use a tube and you put it in a bucket. What you usually do is the diafiltration system. You want to talk about? Huh? Yeah, I took a picture from one of your whatever. I found it. So do you want to talk about it? Give me a break.
Okay. It's essentially like a dialysis, but it's a double membrane, and it's so again you pick your pore size, and utilizing that pump, you can pump through your So you put your sample in the reservoir, and it pumps through that peristaltic pump and goes through your membrane, so it has a larger surface area. And then with some back pressure from the pump, it will kind of force your salt to go out rather than using osmotic pressure, or osmotic, like letting it happen on its own. You use pressure to make it go. And then your salt comes out of that filtrate and goes to waste. And then your sample that can't pass through the pores gets recirculated back in.
In here.
While at the same time, that reservoir creates a vacuum, and you can put another tubing into some water or buffer, whatever you're trying to exchange, and so it drips in water at the same time and exchanges your salt for water.
So you kind of do multiple washes that way, right? Okay. So, and this is diafiltration system, but in industry, if we want to also concentrate the protein, you can use membranes with different pore sizes to do ultrafiltration, microfiltration, nanofiltration. So you can choose the pore size, and I'll show you a chart in a minute here, that you can concentrate and separate your protein based in size from different components within your matrix or extract that you have obtained at the beginning. Okay, so there on a lab scale, I'm mixing languages now. On a lab scale, you can do separation by membrane using kind of a tube that you can centrifuge, and in the middle portion here, there is a membrane that also has different pore sizes. So you can have a membrane with 500 Dalton to 30, 45 kilodalton, for example. And you can separate proteins also based on molecular weight, that way by centrifugation force. So you can put your sample up here and then centrifuge. Whatever is permeable through the membrane will go down and you collect. So anything, let's say if your cutoff is 30 kilodalton, anything smaller than kilodalton will go through. Anything bigger than kilodalton will remain in the upper portion. And you can do several washes to ensure almost all of your components that are less than 30 kilodalton pass through. Yes?
So if you do that, whatever is not passed through, wouldn't that be kind of like, so dry and chunky? So then like, because your water would pass through too.
So then you add more water.
Do you get a lot of fouling and loss?
Yes, so that's why this is not like reusable. So you would use it a couple of times when you are cleaning up a sample, and then you throw it away, and then use it. And you definitely get fouling. Yeah, like you get fouling with your membranes, and you try to wash it all the time. The fouling is a big problem in industry too, especially with using of membranes. Okay, so
how low of the salt concentration do we go with this type of techniques? Like with dialysis, you said we can't go to zero.
no, we can never go to zero. The more you dialyze, the longer you dialyze and the more changes of water you get, you reach lower concentration. But again, sometimes your pore sizes of the dialysis gets blocked. So it's not always a perfect situation. We always get some ash. What's the percentage you're able to get? As
So
well
we're
as
able to remove, like with that system, we are removing 98%
Of
of
the
the
salt.
salt that's added. And then, but it says that if your membrane doesn't get blocked, but we have problems because my protein is very soluble. So once it's in just water and the salt isn't there, it starts to precipitate onto the membrane and clog the pores. So it's kind of a game of cat and mouse, like she said. So like once they're clogged, we're not going to get anything out. So it's like 2% is left.
yeah. Okay, so like I said, there are different membranes with different pore size, and then you can do reverse osmosis where you just water is going through, or you nanofiltration, very small particle like that. These are like ionic compounds can pass through, and then ultrafiltration ranges between 1,000 Dalton to 10,000 Dalton, and then above that 100,000 Dalton and greater, that would be microfiltration. So this is kind of a chart that shows what the size of components you are passing through based on the pore size of the membrane. So here's a milk system just to illustrate what gets separated. So if milk passes through a membrane under the microfiltration, so it has a pore size of 0.1 to 10 micron. So everything passes through except bacteria and fat. So your protein, lactose, minerals, water pass through. If we have an ultrafiltration membrane, the ultrafiltration will prevent the protein from passing. So the protein is your retentate, and what is your permeate is lactose, minerals, and obviously water. If we do nanofiltration, we can get rid of lactose, and then minerals and water will pass through. Reverse osmosis, I retain the minerals, and then basically the water. That's kind of demineralization of the water. Also can be done by reverse osmosis. Okay, so if we look at membrane separation for whey protein, so we get the cheese vat, and then you have your whey as a byproduct of cheese production. If we take that whey, which is the most common production of whey protein concentrate and isolate, is the membrane filtration. If we pass the whey through an ultrafiltration, that means my proteins mostly are retained, and the permeates are mostly salts and lactose. There is some protein, low molecular protein, that would pass through as well. So this is one byproduct. You might hear the whey permeate. It's a byproduct of whey protein production. And they can take the permeate and they can separate the lactose as well through filtration as well. But if we look at this row here, so if I take the retentate, it is a concentrate that has a concentration of 34 to all the way up to 80% protein. So in this concentrate, I still have phospholipids, I still have lactose, I still have some sugars, because it's not a perfect separation. Although lactose and calcium or minerals can pass through, but not all of them will pass through. Some of them will be interacting with the protein and they won't really all go through, unless you do a lot of different washes. And the more washes you do, that's the more energy in the industry and the more cost. So sometimes you cannot. So therefore, you can get a WPC that's 34, but if you pass it more times and washes, you can concentrate it up to 80%. Okay? So if you want to convert WPC to WPI, you take the WPC here and you pass it through microfiltration. So this has larger pore size than ultrafiltration. But in this case, what you're doing is you're separating phospholipids here. You do have some protein that might retain, but most of the protein will go through and you get a permeate, and that permeate is your whey protein isolate of 90% protein or higher. So whey phospholipid concentrate is what Chelsea, for example, works with in the lab, which is called ProCream. It has protein still in it, and it has high amount of phospholipids. Yeah?
Just from like your perspective, why would they not do microfiltration before they do the ultrafiltration?
So if they do the microfiltration, your protein goes here. First, they want to separate as much lactose and calcium as possible. So that's the first step. If you do microfiltration first, then your protein, your lactose, everything goes through. Yeah, you know what.
If it's 34% protein, it's not whey protein concentrate.
It's whey protein concentrate. Whey protein concentrate ranges from 34, so you will find in the market WPC 34, for example, WPC 50, WPC 60, WPC 80. There are different levels of concentrates. Yeah, they're cheaper. WP 34 is cheapest. Yeah. The more you concentrate, that means the more energy you put and the more it went through the membrane, the multiple washes. So that's why it's more expensive. Okay. You can do chromatography to do size, to separate by size as well. So size exclusion chromatography, or separation based on the molecular weight of the protein. So basically the principle here is you fill your column with stationary phase that is inert. So there's no interaction really with the protein. It's just a material that has pores, is porous material. And it has different pore sizes. You can build a gradient of different pore sizes. And what happens is the large proteins will not go through the pore size because they're large. They will travel within the particles and elute first or leave the column first because they're the largest. And the smallest one will enter almost every pore and be delayed and will elute later. So you can separate based on the molecular weight with the largest coming out first and the smaller and smaller and the smallest coming out last. So this kind of technique is helpful for determining the impact of processing on polymerization, for example. If we want to monitor degree of polymerization of a protein, we can run it through the size exclusion chromatography and look at, did we form a dimer, did we form trimer, did we form really large polymer that elutes with your wash or with your void volume. So you can do that. Another application, you can just screen the molecular weight of different proteins in your system and isolate a particular component based on its molecular weight. So Wiley, can you tell the glass what you do? An application to size exclusion here?
I wanted to separate beta-lactoglobulin from their protein, especially, so it mainly contains three proteins. So alpha-lactoalbumin and the beta-lactoglobulin are the two main ones. So the molecular weight of alpha-lactoalbumin is around 12,000 Dalton, and for beta-lactoglobulin is around 18,000 Dalton, but at pH 7 it acts as a dimer. So we generally have a phosphate buffer for this procedure, and we dissolve the protein and pass to the size exclusion column. So you could see initially the large molecules, maybe some of the casein protein or any large molecular weight protein comes out first. Then the beta-lactoglobulin comes. Then see, you could do a separation where alpha-lactoglobulin comes. That's how I separate beta-lactoglobulin. Collect fractions at different time points, so you can optimize it with different pH and see to have a very good separation.
And the reason you want to isolate beta-lactoglobulin is because you want a model system to monitor flavor interaction with that particular protein. Okay. So let's have a look here. Anybody? Huh? What's that? I can't hear you. What? Yeah, why? Size exclusion chromatography followed by cation exchange. Ignore this. I don't know why I have that. It's been there for a long time. Nobody noticed but you, Rachel. Good. Even I didn't notice. Any other thoughts? So what are we looking at? We're looking at 3 different proteins that I would like to separate. If you notice, X and Z have very similar molecular weight but different charge, whereas Y has different molecular weight and similar charge to X. So in simple terms, can we separate X and Y from Z by salt precipitation? Can we? We can. Potentially we can, because you have higher net charge. If I use a low concentration of salt, there is a chance that I would precipitate Z and the other two will remain in solution. Okay, but then if I do the salt and then I have two different molecular weights, can I separate them by membrane filtration or size exclusion or both? Huh? Both. I can do both. Okay, can I separate these two, the plus 5 from plus 2 using a cation exchange? I can. So all of them. The order doesn't matter. Oftentimes you start with size exclusion or membrane filtration, kind of the norm, and then go to ion exchange, but really it doesn't matter. The same, you'll get same end results. Okay, here is an example just to illustrate the complexity of purifying a singular protein. This is something I worked on when I was a postdoc at Purdue. And in this extraction here, we are specifically targeting an enzyme inhibitor, a particular enzyme inhibitor in milk. So starting with milk, you want to get rid of so many different components and end up with just one isolated fraction of inhibitors. And you can see that it is a very sophisticated, tedious isolation protocol that involves removal of fat as a first step, then removal of whey, and using ultracentrifugation to precipitate the casein, because the enzyme inhibitor associates with the casein fraction of that milk. And then from there, you use pH to remove a precipitate and get an acid supernatant, and your inhibitor is in here with other components. Then you add a certain concentration of salt, centrifuge, collect the precipitate, adjust pH, dialyze, lyophilize, and resolubilize in buffer, and then again salt concentration, then you centrifuge, precipitate, you collect the supernatant, you dialyze, and you end up with your final supernatant. It's such a long process, probably a day worth of work. So just to illustrate that fractionation of protein can be super annoying process. Okay, I'm going to give you a 5 minutes break to stretch and go somewhere and come back in 5 minutes, or just stay.
What is the most common method of separation in industry?
The most common method of separation? It depends on which protein. Every protein is different. For whey protein, membrane filtration is the method. It's the least cheap. For soy protein, it's alkaline extraction. What else? Mostly for plant-based protein, it's mostly alkaline extraction and pH precipitation. And for dairy, it's mostly membrane filtration.
Okay, I'm asking because for my project, I'm working with gommacacia. And I want to separate or to get the fraction, the protein fraction from gommacacia. And that fraction is 2%.
Okay.
Of the entire
entire.
gommacacia. So it's a little amount of protein.
Yeah.
So
What's the source of that protein? Gum acacia?
Yeah.
Okay,
So
so
I
it's
have the
just
gum, and most of the gum is a carbohydrate, but it has only 2% of protein.
yeah.
So we know that that protein is in charge of, or it acts as emulsifier. That's why gum acacia acts as emulsifier, because it had that small portion of protein. So
But
that
I thought gum acacia itself is emulsifier.
yeah, but it's because it has that protein, because that protein has the ability of react with the oil or with the hydrophobic,
Yeah.
and the rest of the gum acacia is a carbohydrate, which is going to be hydrophilic. So we want to separate that small portion. So I actually read some papers about ion exchange, hydrophobic interactions, but of course the columns that they use are tiny. I mean, they're very small, and I will need, because I want to take that protein, I want to extract that protein, and I want to take that protein and spray dry oil. And to spray dry oil, I need at least 30 grams of that extract.
So what you can do is, instead of using a column that you buy, you pack your column like Vidi does. But instead of he's doing size exclusion, you can pack. We have hydrophobic interaction chromatography, stationary phase media, and then we have large columns. So you can actually inject large amount of sample and collect reasonable amount of sample. You would have to inject several times in
Several
order to
times,
get
yeah.
30 grams.
So you guys have that column?
Yeah, we do
So
have
just
the
like a
media.
glass
The
or
column is Vidi
the
using
one,
that. I don't know if he's done using it or not, but you guys can work something out where you would just have to fill the column with the hydrophobic interaction chromatography media.
Okay.
Yeah.
Okay. And then, because we were thinking with Gary about using the membrane too.
Yeah.
Do you know there are like big? Because you showed the picture that there is like a tube and there is a membrane in the
Yeah,
middle.
you can. They can
Are
come in
they-
different sizes.
But yeah, the big tubes where I can load and big
Well, you can
amounts.
get tubes that are bigger, big tubes, but they're also what do you call them? Discs with
With a
membrane
membrane.
that can come also in different sizes, like what
4
Rachel
size.
is doing. Then you can pump through and separate.
The protein.
Yeah, yeah.
And do you guys have that in the lab? Do you know?
We do. Rachel is using it.
It's a small.
It's like the cassettes are this big, and I think you might want to ask Rachel how many grams she processed at one time. It's very lengthy, but the column would be easier.
The
The hydrophobic
Hydrophobic,
interaction
the
chromatography
one
will
that
give you
Vidi
better yield.
okay.
Yeah.
Okay, I will ask
Yeah.
him. And then you have the media. So that's the thing that I have to pack my column.
Yeah,
with
you
that
have to
media.
pack. I think we have the media. I don't know where it's stored right now.
I
Maybe
can ask
Lucy
them.
or Sonia. No. Yeah, so we can show you how to pack a column.
And then I will have to use different amount of solutions of salt, right? Because I want to, the protein that I have, it has different fractions. The protein that I want to get has different fractions, and there are 3 fractions mainly, and there are 2 that I'm interested on.
So you have to do
Try
trials. I mean, it's not. It's always you have to run and see if you get the protein out first, and take that fraction as one fraction and determine the purity of that fraction. To know if you really got your protein away from the other carbohydrate. If they're tightly bound together, it might be really hard to separate them. So first you have to run a trial and see if you get a protein fraction that is mostly protein. And then from there you can start playing with the gradient and changing the gradient to see if you can fraction. Or you can take that fraction and use a different type of chromatography to separate them. You can do size exclusion to separate them if you know that they're different in molecular weight. Or you can use if they're both, all of them have similar surface hydrophobicity. There is no way you can separate them with hydrophobic interaction chromatography.
Yeah, I know there are some papers where they have
Yeah.
done that, but it's just that it's like tiny amounts of
Yeah.
what they get, and I need at least 30 grams to be able to use that to spray dye my oil.
Yeah, I thought you were going to work on pea protein.
Yeah, I'm working on that too. So it's kind of crazy. Yeah, I'm working on 2 of them.
Okay.
Yeah. Okay. Thank you.
All right. All right.
Should I
Let's.
email you about the chromatography if you're
Yes.
offering?
Yeah.
Because I haven't seen it. Don't know what it is. Yeah.
So I can direct you to the church.
That'd be great. Yeah.
And then you can, I think it's available through the library.
Oh, really? Oh, okay.
Yeah, then you can distribute that chapter. I like
Yeah.
So you can review that chapter, and if you have questions, we can set up one-on-one.
Okay. I'll probably just email you regarding the chapter name. Or, sorry.
Yeah, we can start there, and you can review, and then we can sit down and talk.
Awesome. Thanks.
All right, are we all here? Who was sitting here? Did we miss somebody? So, Vaidehi. Okay. All right. So I have few recap questions, but yes.
So for size exclusion chromatography, if you have 2 proteins which have the same molecular weight but the different shape, like globular and fibrous, which
You
one-
can separate them.
which one has?
A faster will go to globular. So if you have an open structured protein, it will be hindered, so it won't go through the pores easily. So globular protein and an open structured protein of similar molecular weight can be separated by size exclusion. Good question. Okay. So recap questions for you to think about. We just covered this, so it's not worth it to go through these right now. Any questions do you have of anything we covered so far? Yeah.
I was wondering, like you mentioned, there will be more beta-lactoglobulin by ion exchange method.
Yeah.
That yield. But do you know what's the reason for it compared to the other?
It depends how they interact. Beta-lactoglobulin and alpha-lactoglobulin, how do they interact with the ion exchange? So you might lose alpha-lactoglobulin more because it won't interact as much with the column, and you retain more beta-lactoglobulin. It's just basically based on their charge and how they interact.
And for the filtration, actually you definitely will get higher alpha-lactoglobulin because they interact.
With the membrane, it's based on size. And
Yeah.
beta-lactoglobulin and alpha-lactoglobulin are very close in molecular weight. So if you use ultrafiltration, you will be able to retain both of them. Okay. So far we talked about protein quantification and then protein isolation, separation and isolation and concentration. And now we're going to move and talk about protein structural characterization. So looking at structural components of the protein or structural characteristics of the protein and identifying proteins. So when I say structural characteristics, what can you think of? Amino acid composition, yes. Okay, what else? Amino acid composition and sequence. That is a structural component. Yeah? Secondary structure and tertiary structure, so molecular configuration. Very good. What else? Surface properties. Excellent. What else? With surface properties, we can say surface hydrophobicity, surface charge, surface sulfide groups. These are all surface properties. Okay, so we have amino acid composition and sequence. molecular configuration and denaturation state. With molecular configuration, we can say a secondary structure and tertiary structure and quaternary structure. Denaturation state is determining the impact of processing on the unfolding of the protein. Molecular size, not just amino acid composition and sequence. What is the molecular weight of the protein? And how would the molecular weight change if polymerization occurred based on processing? We talked about surface properties, molecular interactions. So are we forming polymers via hydrophobic interactions? Are we forming polymers via disulfide linkages? Are we forming interaction with carbohydrate? What form of interaction? Is it covalent or is it charge-based? What type of interaction is occurring? Okay, another characteristic is the functional properties, and we will talk about that in a separate lecture, talking about functional characteristics of the protein. And these we talk about physical properties and biological properties. So in terms of physical properties, it has to do with the structure and matrix. So physical, we can gelation or emulsification or foaming, for instance. Biological, it can be protein digestibility, essential amino acids, bioactivity of the protein. Okay. So there are so many methods that we will go through to characterize a protein. There are structural methods and identification methods. So we're going to talk about a lot of these methods. And this is just to remind you of this. Again, this is the theme of the course, is linking structure to function. And what impacts protein structure, we talked about it earlier, the composition, the sequence, ionizable groups, hydrophobicity, conformation, molecular interactions. All of these impact is the molecular configuration, the tertiary, secondary structure, and the formation of associates or molecular association, forming of quaternary structure. The size of the protein is impacted by the amino acid sequence. How many amino acids do we have? And that will dictate molecular size. The association of the proteins into dimers, trimers, hexamers also impact the total molecular weight of the quaternary structure. And then the ionization and hydrophobicity impact surface properties and how they would interact, how the protein interact in the environment with water, with salts, with sugars, with fat. So that. So I'm going to give you some examples about why is it important to look at structural changes of the protein in terms of applications, real-life applications. So why do we characterize the protein structure? Why do we monitor protein structure? So, for example, during processing, so if we are producing high-protein beverage, for example, and we are processing the beverage under different conditions, so we want to determine the shelf life of our beverage. We want to anticipate if the protein beverage is going to last 6 weeks on the shelf, is it going to last 8 weeks, 12 weeks? So how do we anticipate or predict that? We look at the protein structure and how it's impacted under the same processing conditions for beverages. So if I want to formulate with whey protein, conditions will impact whey protein differently than it might impact pea protein or soy protein. So if I want to formulate with a new protein and replace whey protein in my beverage, which is the golden standard for protein beverages, I really need to understand how that processing of my beverage is going to impact protein stability or pea protein stability. So I take the pea protein and I treat it under the same thermal treatment conditions, and then I look at denaturation, rate of polymerization. And then I go, okay, if I prepare 5% protein beverage with pea protein, it's going to fall out of solution in 3 weeks. It's not going to work. Why? Because the protein denatures faster, is more prone to polymerization because it has higher surface hydrophobicity. It's a larger protein than whey protein in terms of molecular size. So that is one example. Another example for monitoring structure and function is valorization. Whey protein comes from essentially a byproduct. So a few years ago, whey was discarded or used as animal feed. And then for some reason, they figured that there's a lot of whey that is being generated. Can we make use of that? So they looked at the components of whey and they found that it has a very functional protein in it. And then it became now, whey protein becomes the most expensive protein ingredient. It started with a byproduct, but looking deeper into the structure and function of the protein resulted in production of an ingredient of a high value. And that's the word valorization, is increasing the value of a byproduct. So now they're looking at canola protein, for example. Canola is an oil seed. So they're producing a lot of oil, and then they end up with a meal, and that meal goes to animal feed. So same with soy. 50 years ago, it was the same situation. There was meal that goes to animal feed, and there was the soybean oil. And then they soon discovered that soy protein is highly digestible, is a complete protein. It can form very good gels. It can emulsify. So they found the value of the meal, and they extracted protein from the soy meal. So canola is going in that direction now. So the same thing, we're producing canola oil, we're ending up with a lot of meal, and then looking at the structure of the canola protein will help with increasing value of a new ingredient. Oftentimes, you want to produce an ingredient, and a protein ingredient, and there are so many steps until you get an isolate. Especially if you start with a really complex crop, oilseed, for example. There is the crushing of the oil. First of all, there's the conditioning of the soy. They condition the soy, they flake the soybean, then they crush the soy flakes, then they add hexane to remove most of the oil, and then they have to dry the hexane. So there's so many different processing steps that might impact the structure and function of the protein. So monitoring what happens to the protein structure at each processing step can allow for optimization of the process to reduce structural damage to the protein and get an ingredient that is still functional. Comparison to competitors' products. This kind of was the first project I worked on when I did my sabbatical at Cargill. So they are getting into the pea protein business, but there are like over 20 different companies that are selling protein ingredients. So they wanted to partner with one of the companies, but they wanted to understand how they can sell this product to their customers. So in order to understand how they can sell their product and attract their customers to buy their product rather than the 20 other companies, we had to look at the structure and function of 20 different protein ingredients in order to understand how they're different. And when we understand how they're different, we can explain the functional differences between Cargill's product versus other competitor products. Change in functionality can happen during processing. Why? Because in industry, they install new drying technologies or drying apparatus, new cooking equipment. So once they change from one equipment to another, it might impact the functionality of the product that is being produced. So looking at how changes in the production in terms of using different equipment is very important because they really want to maintain structure and function, but sometimes things happen that they have to replace equipment. How would that impact functionality is important by looking at changes in structure. Functional enhancement. This is a big deal right now, especially with the theme of replacing dairy and meat protein with plant protein. Plant proteins are not as functional as whey protein or casein or egg or even soy protein. Some of the new plant proteins are not functional as soy. So looking at ways to enhance functionality by changing the structure of the protein, by doing something to the protein, hydrolyzing it, glycating it, treating it with pressure, or treating it with cold plasma, or doing something to the protein to change the structure so that you impart a targeted enhancement in functionality. Looking at structure and interaction with other constituents. When you formulate food, it's not in void. It's not just proteins. You have the water, you have the salts, you have the sugars, you have the fat. Under what conditions you get what sorts of interactions? Some interactions are desirable. To form an emulsion, the protein and fat are interacting, so this is desirable. But sometimes you form Maillard reaction products, it's not desirable. So you have reducing sugar that interacts with the protein. So understanding the conditions that would result in changes in the structure of the protein and interaction with other constituents is really important in different food systems. Okay. So now that we established that protein structure is important, let's look at ways that we characterize the protein structure. So there are chemical assays as well as analytical tools that are instrument-based. So the chemical assays, I categorize them into different test categories. So we can look at aggregation and molecular distribution. We can look at surface properties. We can look at chemical deviation. So if we look at aggregation and molecular distribution, we can do that using gel electrophoresis. So with gel electrophoresis, we're actually looking at the different components within a protein mixture, looking at the different subunits, looking at the molecular weight or estimate of the molecular weight. If we solubilize our sample in different buffers, we can predict the interactions that happen. That means if I solubilize my sample and add the reducing agent, then without reducing agent and with reducing agent, I can see if I had polymerization due to disulfide linkages. Because if I run it without reducing agent, I will see large molecular weight polymer. When I add a reducing agent, it will break. If I see it break into two subunits, that means that we had disulfide linkages that caused the polymerization. So I can predict some sort of interaction that led to polymerization. I can predict the different or find out the different components that are present in my protein mixture. So very briefly, we have three main types of gel electrophoresis. STS, that it's called STS because we are solubilizing our protein in STS, in sodium diducyl sulfate. And urea, that means I prepare my sample in urea and then run the gel. Native polyacrylamide gel electrophoresis, I don't do anything to the protein. I don't solubilize it in STS or urea, just water and run it. So, and this is native because STS result in denaturing of the protein by breaking non-covalent bonds and imparting a net negative charge on the protein. By having a net negative charge on the protein, when I run the voltage to run the gel, all of them are going in one direction, going through the porous gel based on molecular weight. In urea page, then my sample, my protein is running and separating based on charge to molecular weight ratio. Okay. Have you are you all familiar with the gel electrophoresis? Okay. So basically what you have is you purchase a cassette that has a gel embedded in it, and you have wells, and in each well you can inject a certain amount of sample, and then you put it in a chamber, you add a running buffer, and then you run voltage, and the proteins will separate through the gel. If we're running STS page, it's separating based on molecular size, so larger proteins will migrate slower than smaller proteins. Okay, so after you run the gel, you break the cassette and remove the gel, and then you stain the gel by Comasi blue, so it is stains the proteins. You destain, and then this is what you see. So every protein component or an ingredient, it will have multiple protein subunits. So you can see the different subunits, and you run a standard with known molecular weight, so you can really predict, or not predict, estimate the molecular weight of the different components. Here, for example, this is soy protein, so we have beta-conglycinin and glycinin as the main components, and beta-conglycinin have 3 main units, and glycinin has 2 main subunits. So you can actually see the different subunits within soy protein. Okay. So in STS page, sometimes you have to use a reducing agent, and reducing agents breaks disulfide linkages. So that means it reduces the disulfide linkage. And this sometimes is really important, because look at this. This is soy protein. Soy protein exists as a quaternary structure. We'll talk more in detail about soy protein later. But what I meant to say here is that one polymer of soy protein contains 12 different subunits. 2 of these subunits are bonded by disulfide linkages. If I run them on the gel without a reducing agent, this is what I would see, a smear. I won't see the clear separation of my subunits. For soy protein specifically, I have to break these disulfide bonds so that the protein subunits will migrate separately, and then I can see each subunit individually. So for soy protein, it makes no sense to run the gel without a reducing agent. Whereas in whey protein, for example, you don't need that. Native whey protein, you don't need a reducing agent to separate it on the gel. If a whey protein, you're looking at the impact of thermal treatment on the polymerization of whey protein, you run it without a reducing agent, and then you run it with a reducing agent. Then you can see if you had caused disulfide interchange or linkages due to thermal treatment. Yeah? Okay. So in this gel right here, if I want to determine the impact of using specific enzymes, and I want to know the enzyme is targeting what subunit. So if you see here, I have soy protein isolate, and then this has been treated with papain. So the papain hydrolyzes specifically beta-conglycinin, and then this has been treated with pepsin. Pepsin targets glycinin subunits. So the aim for that is if I hydrolyze glycinin, I enhance the emulsification of soy protein. If I hydrolyze beta-conglycinin, I enhance the gelation properties of soy protein. So the gel helped me determine the specificity of the enzyme by being able to see what the enzyme targeted. These subunits disappeared. That means they hydrolyzed, the enzyme hydrolyzed these subunits, and here subunits disappeared. That means the enzyme pepsin hydrolyzed was specific for glycine. That's just one application of the gel. It's stuck. I'll be right back. Sorry. Okay, another form of electrophoresis is the isoelectric focusing. In this case, what you do is you also have a polyacrylamide gel, but what you run on the gel is amphilites. Amphilites are a group of polymers that carry positive and negative charges. So you load amphilites and then you run a voltage. So the amphilites are going to migrate based on their charge and form a pH gradient. Then you're going to inject your sample and then run the voltage again, and the sample is going to migrate until it reaches the pH at which it will precipitate, because it's the isoelectric point of it. Then you separate them based on their isoelectric point. Now, what's the benefit of having isoelectric focusing? Is oftentimes we do it so we can run a two-dimensional gel electrophoresis. Often proteins can be similar in molecular weight. Some proteins are similar in charge. So to enhance the separation and identification of the proteins, we separate them first based on their isoelectric point, and then we run them on a regular SDS gel and separate them based on size. If you see here, these two proteins, if we ran them on a regular SDS gel, they won't be separated because they have the same molecular weight. If we ran just the isoelectric focusing, these two proteins would look like one band. But when we run the size exclusion, separate by size, then we can see that there are two proteins. So it's enhancing the separation of protein for better identification. And here's an example of a gel that was run with one dimension. And here's our soy protein, for example. We run it in one dimension and take that one sample and run it again using isoelectric focusing and then separation by size. We were able to see this has the same molecular weight, but there are like 5 different subunits here. And then here also you have same molecular weight, but then you also have multiple different subunits. So we were able to see multiple subunits when we did 2 separations. And this here, this band here is basic subunits, because then when we ran it, here's pH 10, so these are basic versus this is acidic subunit of glycine. We were able to differentiate the acidic from the basic subunits. Capillary electrophoresis, this allows for quantification, not just a qualitative detection. So you have similar principle to gel electrophoresis, where you're separating based on isoelectric focusing. So you have a capillary tube, so you can have ampholytes run through a gel, and you can separate the proteins based on their isoelectric point. Or you can run a regular acrylamide gel, STS, and separate based on size. Or you can have just diffused silica, where it has negatively charged groups, and then positive charges from the buffer will be attracted to the negative charges on the capillary. And then all of your proteins will be dragged with the positive charge. So you separate positive first, negative, and then neutral. And then they go through, and then you have a detector similar to an HPLC detector, so you can actually quantitate. Surface properties. So looking at surface hydrophobicity, this is a chemical assay where we use a probe, a hydrophobic probe, ANS probe, that we will bind with the protein. And it is, they bind to the protein via hydrophobic interaction, but this probe is a fluorescence. So you can measure the fluorescence. So the more surface hydrophobicity you have, the more amount of probe will bind to the surface, and you have higher fluorescence. So then you can determine surface hydrophobicity that way. So it estimates the changes in the structure of the protein due to unfolding. So if the protein denatures, you expect to have higher surface hydrophobicity. Sometimes you hydrolyze a protein. When you hydrolyze a protein, you may expose hydrophobic components, or you might expose charges on the surface. So the surface hydrophobicity, depending on the type of enzyme that you used, might increase or decrease. So oftentimes, we use it to compare different proteins, to compare whey protein to soy protein to pea protein, and explain their differences in solubility. If you have changes in solubility, it could be directly related to how much hydrophobic they are on the surface. And oftentimes, monitoring surface hydrophobicity during processing can also indicate if we're forming polymers. If we're denaturing, then forming polymers. So let's say I want to determine the impact of processing time, thermal treatment on surface hydrophobicity. So surface hydrophobicity and then heating time. Let's say 5 minutes, 10, 15, 20, 25, etc. So we're starting with a certain, at 0 time of heating, we have a certain surface hydrophobicity. And then as you heat, let's say at 75 degrees C, whey protein potentially will denature. So as you heat, you have an increase in surface hydrophobicity because the protein is denaturing, exposing hydrophobic groups. So this is increasing until we reach a maximum. And then with more heating, we notice a decrease. What's happening here? Why is the surface hydrophobicity decreasing? Again. Yes, so what's happening here, protein is denaturing. So we have protein denaturation. Here we have protein polymerization. So the protein is denatured. Now the protein is polymerizing via hydrophobic interactions. The probe, the ANS probe, is no longer binding to the hydrophobic surface because now the proteins are interacting with each other. So that goes down. Surface charge is also is impacted by processing, so we can monitor that as well. And changes in surface charge impact solubility, impact emulsification properties, surface properties. So this can be done by measuring zeta potential using an instrument, but it also can be done using titration method to determine the surface charge. Free sulfhydryl groups, it has an indication of potential to form disulfide linkages. And as the protein denatures, some embedded sulfhydryl group within the interior of the protein can be exposed. So if this is exposed, this is another indication of unfolding and potential polymerization of the protein via disulfide linkages. Chemical deviation, it changes in, for example, in the extent of amine blocked by the Maillard reaction. We talked about that previously. So if we are processing and Maillard reaction occurred, it might damage lysine because lysine will be the one interacting with the reducing sugar. So we can actually measure before processing and after processing, determine the level of amine that was blocked by interacting with the sugar. So OPA react with the free amine and give you a fluorescence, and you measure that. When the amine is blocked by a carbohydrate due to Maillard reaction, OPA will not be able to interact with it. So you see a decrease in free amine, and then you can calculate percent blocked. Okay, should I release you? Okay, I hope to finish this, but next time. All right, good stopping point. What we'll do next time, here's the plan. I thought we were going to do this today, but we ran out of time. There is the practice problems that I posted online for protein separation and characterization. After I finish, I have 20-some slides left. We will take 20 minutes like we did last time, yesterday, and answer those questions and then start a new topic. Okay? That's next week. Thank you. Have a good evening. Happy Valentine.